we're going to be using the derivative to tell us something about the maximum or the minimum of a function. That's why I like this one, minimum effort and maximum result. Because yeah, we can find something called global or local maximums or minimums. I just want to explain those a little bit just before we get started. So a local maximum is a place where, yeah, if you just zoom in on the area, it's like this right here, for example, is called a local maximum. I'll just say max for short here. So that's because in the local area there, it's a maximum. But it's not the global maximum. That's like the overall one. So that would be the global max. Well, it's also a local max as well, right? It's a local, but happens to also be a global max. And this right here then would be a local min. It's a local minimum because around its area, it's a little minimum area there. So at least this is just the idea behind local and global max and min. Let's look at how to use the derivative for it. Now, remember what the derivative tells you. The derivative tells you about the gradient of the tangent line. So let's look at like maybe this point right here. At this point right there, now let me just draw a tangent line, something like this right here. This here would be the tangent line there. In other words, at this point right here, we know that the derivative f prime of x equals 0. It's flat here. The gradient of the tangent line is 0 here. And can you see there's another place where it is? It's right here as well. That's another place where there's a place where the derivative equals 0. So I'm going to say right here, because the gradient of the tangent line is 0. So that means there's another place here where f prime of x equals 0. Okay, so this is this area right here. So a stationary point is where the derivative f prime of x equals 0. So you might think, oh, that's great. So stationary points are it, right? That's just where the derivative equals 0. Not quite. I mean, this is what we call a stationary point, it's true. But stationary points aren't always maxes or mins. So I'm just going to write this down. I'll say maybe not always. There exists places where maybe it's not. So I don't know, let's say a graph like this one right here, if this is x, this is y. And I do some graph of like x cubed, something like that. I mean, it goes like this here, for example, x cubed. Well, technically the derivative equals 0 right here, but it's not a max or a min. So this right here, it's not a max or a min. Not a max or a min. So that doesn't work. So there do exist places where, you know, that won't work. So things like this can happen. So it's not always. So stationary points aren't always maxes and mins. So we have to be a bit more specific if we're going to define a maximum or a minimum. So we're going to do that now. A local max or a local min is where the derivative is 0, just like we said here. And, this is going to be the important part, and the derivative changes sign from left to right. Let me explain what that means here. So if you look at this example right here, let's just say right here. Let's see here. What is the derivative? So this right here is a place where the derivative is 0. That's true. But also, if you look to the left of this point, we have that the derivative is positive. Can you see like things are going sort of upwards like this right here? And over here, things are going downwards. So if it goes from going up to going down, then it must be a max. Just like right here, for this point right here, to the left of it, the derivative is negative, so it's going down. To the right of it, though, it's going positive, it's going up. So do you see it goes from down to up? So do you see the derivative changed signs? So this is what's really important here, okay? You can check the derivative changing from left to right with a sign diagram. Now in applications, you don't have to do this strictly, but in analysis you do. I'm going to show you anyway because it's not such a hard thing to do. I'll show you with an example maybe. So we'll find the max or the min. By the way, I like this joke right here by Chris Rocker. I used to work at McDonald's making minimum wage. You know what that means? It means that your boss is trying to say, hey, if I could pay less, I would, but it's against the law. He's right. All right, let's try to do this one here by hand. Because, of course, we could use a calculator maybe, but let's try to do this one completely by hand. Let's find the max or min point of this function right here. Well, this looks like, I mean, you can already kind of guess a little bit because it's a quadratic, which means it's going to be a parabola. I know it opens downwards because of the minus, so I know it's going to be like this. So I know this is probably going to be a maximum. But let's pretend we didn't know all that. So what do we say about the maximum or the minimum? At a max or min, what happens? Remember, on this right here, the derivative equals 0 at a max or a min. Actually, we should say it right here, actually. Derivative equals 0. and it changes sign. So let's first of all start by setting the derivative equal to 0. So we're going to set the derivative here equal to 0. So we're going to say f prime of x. Let's actually find it. Let's go ahead and figure that out. So let's see, the derivative is going to be 2 times minus 2, because the exponents come down. It makes it minus 4. X to the power of 1 plus, and this here will just become an 8. And the 6 disappears, goes poof. Right? If you're careful with your exponents, this is what you'll see happens. The 1 comes in front of the 8. And then this becomes 1 less, which is 0. That means this cancels out and becomes a 1. So here we go, we got this. So we have that 0 equals minus 4 times x plus 8. Does that make sense? We're taking our derivative and we're setting it equal to 0. That's the key here. The key is we're setting our derivative equal to 0, because our derivative is that. So because of that, then I move my minus 4x over to the left. So I have 4x equals 8. Therefore, I have x equals, let's see, 8 divided by 4, which is 2. So now I know x equals 2 is the coordinates of my max or min. Well, that's the x coordinate. Do I know the y value? Let's go ahead and figure that out. What's the y value? Now keep in mind, you have to put this into f of x, not into the derivative, okay? So you have to put this into f of x. Because see, this derivative just helped me to find out this x value. But I'm curious now, when x is 2, what's y? Well, my entire equation for y is f of x here. That's what tells me this. So it's going to be minus 2 times 2 squared plus 8 times 2 plus 6. Let's keep going. Let's see, 2 times 2 to the power of 2 is just 2 times 2, which is 4, times minus 2, which is minus 8. Let's see, 8 times 2 is 16 plus 6. Now 16 minus 8 is just 8. So 8 plus 6, right? So therefore, I can say that y equals 14. So then I know that my point must be 2 comma 14. This must be my answer. Okay, so this here is my max or min. And if we really want to figure out if it's a maximum or a minimum, let me show you how to do what's called a sign diagram. So let me show you this. This is the piece that you need if you're in analysis. But it's a good thing to learn and look at. So sign diagram, what do we do? Well, we just take this right here and we make a little line here. Maybe I'll put a little thing right here at x equals 2. Now I'm looking at f of f prime of x. That's what I'm looking at on the y-axis. Now this value right here is x. These are the x values. But up on the y-axis, I'm looking at f primed. So I know that the value here is 0 at x equals 2. The derivative is 0. Right? I found that. I know that. Look, here's my derivative is this function right here. My derivative is, let me just write it down here, f prime of x equals minus 4x plus 8. Do you see that's my derivative equation there? So when x is 2, minus 4 times 2 gives me minus 8. Minus 8 plus 0 plus 8 gives me 0. So that works. I've got to check a point to the left of it. So what's something to the left of x equals 2? Maybe I'll check at 1 and I'll check at 3. Do you see that? So at this point right here, this is, I don't care about this one. I'm just checking over here. What's the gradient do? Now I don't care about the actual value. I just care about the sign of it. So watch carefully. At x equals 1, minus 4 times 1 gives me what? So let's just, so f primed at 1. What does that give me? Well, let's see. Minus 4 times 1 is minus 4. Minus 4 plus 8. Is that a positive or negative? That's a positive. That means I know my graph goes something like this. It goes up over here. It's going sort of upwards. It's rising. It's increasing. How about over here at 3? Well, at x equals 3, let's see here. So f primed at 3. Let's see here. 3 times minus 4 is minus 12. Minus 12 plus 8 is a negative value. So that means it's going down. Do you notice then if it goes from up to 0 to down, the graph must be doing some shape like this. Therefore, this must be a maximum. Do you see how we figured that out? We figured that out by just looking at the derivative to the left, look at the derivative to the right, and it changed sign. Look, it went from plus to minus, from left to right. So it just has to change sign from either side of it. So now we know for sure this is actually a local maximum. In fact, it's a global maximum. That's not as important. That we know this is a local maximum. Now you might wonder, why don't I just use your calculator for this? Because this is super easy to do on a calculator, isn't it? Look, I can just say, all right, here's my graph. Give me the graph of minus 2x squared, all that stuff. I can do all that stuff right here on my graph. But sometimes the questions are a little bit sneaky. This is the idea here. That sometimes they're phrased in such a way where you can't just use your calculator. So let me show you this. What if it's phrased like this with some k value? Ooh. And they say f of x has a local minimum when x equals 1. Find k. Uh-oh. Using your graph won't help you here because your graph doesn't know what to do for k. I mean, I guess you could do this on your TI Inspire and guess for k, but let me show you how to properly do this. We're going to use this idea then that, well, local minimum, what does that mean? That means f primed at 1. We know that that happens, right? When x equals 1, we know that the derivative is going to be 0. So let's find the derivative at any point. Let's just find out what f primed of x is. So we'll do the derivative here. Let's see. It's going to be 3 times x squared, all that over 3, because the 3 comes in front. This becomes 1 less. Plus, let's see here now. 2 times 3 is 6. X to the power of, let's see, 2 minus 1 is just 1. So there it is, over 2. Plus, let's see, this here just becomes k, because there's an x to the power of 1. 1 times k is just k. And this becomes then x to the power of 0, which is just 1. And this one here disappears, goes poof, goes away. Let's simplify our derivative a little bit, because we can. Let me see here. The 3's will cancel out here. That's kind of nice. And the 6 over 2 gives me a 3. So then I know that my derivative then at any point is x squared plus 3x plus k. I will use this. This is my derivative at any point. But I know that when x equals 1, do you notice this right here? So at x equals 1, I know that this whole thing equals 0. So I can say 0 equals, because that's what happens at a local minimum. At a local minimum, the derivative is 0. So I'm going to set this and say, 0 equals 1 squared plus 3 times 1 plus k. I don't know if that made any sense. I'm just using the fact that a local minimum, that happens when the derivative is 0. So I first found the derivative. Now I know I can set the whole thing equal to 0 when I'm at x equals 1, because I know that's a minimum. Well, a minimum or a max, the derivative is 0. So I keep going. You'll see this isn't actually so bad at all. So 0 equals, let's see, 1 squared is just 1. 3 times 1 is just 3 plus k. Therefore, 0 equals, let's see, 1 plus 3 is 4 plus k. So that means k must be, well, I can move my 4 over. K must be minus 4. We're done. Do you see this wasn't nearly so bad as you might think? This kind of question, I hope you'll see, it's totally doable, isn't it?